And at the same time, with that, I will open the 5.4. Okay. All right, and there we are there. Now I've cut off my attendance lists, and hopefully I'll see them if they come in, but if you see someone trying to come in, because I have too many things open, I won't necessarily see it as quickly as you will, so please let me know if you see that happening. Oh, I have 11 people now, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I'm missing somebody. So let me go on and see who that is. Ah, LaRon's trying to get here. Let me see, there you are. Okay. Okay. Now let's see. Should be 11 now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Okay, there's LaRon. Okay. All right, I think, oh, here comes Jermanuel. So let me get Jermanuel in. All right. So that's up to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Got it. Okay. All right, good deal. Gave you a little bit of time to think about. Do you have anything that you want to air, share, disseminate, anything before we get started today? Oh, LaRon has a big LSU background, huh? All right, I don't know. Guess we'll let them stay in the class, though. Okay. We won't take it to a vote, though. I'll make a command decision and let them stay in. Okay. Let's see. Going to start the slideshow from here. We are recording, so we'll start from current slide. I'll try to start from current slide. There we go. Now, and it advanced the slide after all. Okay. So I'm going to minimize the screen, or at least I'll do something to it if I can get my cursor in place. Okay, if y'all see anybody else come in, let me know so I can try, because I have so many things open I won't necessarily see them as quickly as you will. All right, if you have no announcements, I have, oops, here comes somebody. Kyle is here. Okay, we won't take that to a vote either, whether we let him in or not. Okay, Kyle is here. Okay. At least he's trying to get here. And let me make sure that would be 13 in the class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got it. Okay. Okay. So, why does that keep popping up? I'm not sure, but we'll live with it. All right, here's my announcement. If y'all don't have any, oh, here's somebody else. Kirpa is coming in, so let me get her here. All right, and Anita is on the way. So let's get Anita here. What's that? I can't hear. Were you talking to me or just had the microphone on?
Just microphone on, sir.
Oh, okay, no problem. Okay, so let me make sure I've got everybody still. Now we're up to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Got it. Okay, and again, if you see anyone else trying to get in, let me know and I'll admit them. Now, I have a little bit of an announcement. If none of you have anything you want to share, here's one. Hopefully, it's not going to be an issue, but it could be. And here's what it is. Wait just a second. I need a little more light in the room. It's plenty bright outside, but this is a northeast corner, and after the morning hours, it's not necessarily so bright in here, especially with me in there. Okay. Hopefully this won't be an issue, but it might be, so I just wanted to let you know before Monday, okay? This weekend we've got to make a trip over to Georgia. We're leaving very early. Eat your heart out, Kyle. Okay, Kyle's from Georgia. We're going to be leaving very, very, very early Friday morning. My wife is a infectious disease epidemiologist, and she figures we're going to have to stop at least once. The earlier we can leave, hopefully if whatever place we stop has cleaned overnight, fewer people will have been in there to touch it, and fewer people will be out and about. So that's our reasoning for leaving extremely early. And what it is, I grew up on a farm in Georgia, and after my parents died, the farm was left to the four of us siblings, and we've kept it sort of as one big farm, but over the years, my two brothers who still live over there, they basically got tired of the work of a farm and the constancy of it, and they're getting old, so they've sold the herds, the cattle, and sold a lot of the equipment, and we planted trees. And trees don't take a lot of care, but Karen and I decided to put on our part of the land about 400 hardwoods. Most of the people just plant pines, but we decided to do 400 hardwoods just to have them look good and to be there. But hardwoods take a little more nurturing than pines do, and they're a bit more expensive too. So we've got not a huge, but a little bit of investment there. And with the very, very, very rainy spring we've had and early summer, the grass has gotten tall, and we need to spray around the trees to knock back the competition. Because even though we've had a lot of rain so far, July and August are coming, and those are typically very hot, dry months. As if it's not hot enough out there in June, but it is. But we have had rain. So we want to knock back the competition. So we're going to have a long working weekend there. Which means we probably won't leave Sunday night, because then if we had to stop, we'd have to be stopping at places that people have been there all day. So we're leaving very, very, very early on Monday morning, and hopefully we'll be back here before 11:30 when this class starts. However, if we run into problems, as in traffic around Atlanta or something else like that, we may be a little late. And I don't know that I'll be able to get in touch with you to let you know that. I'll have my cell phone, but sometimes service goes in and out. If I can get on the system and cell phone, I'll open it up that way. I don't know that I'll be able to, though. So if you log on or try to log on Monday morning and I'm not here, hang on. I will be here just as soon as possible. Hopefully we'll be here. We're going to leave early enough that hopefully we will be here by class time. Okay, so that's my little announcement. Have you got anything else you want to share before we get started on today's class? Okay, if not, we are in Chapter 5, Integration, and Section 5.4, the Fundamental Theorem of Calculus. All right, we're on page 321, and the topic at the top of that page, the average value of a function. Now this builds on what we were just doing with the mean value theorem for integrals. Okay, so the average value of a function can be derived this way. I think we just about got started on it last time, but my PowerPoint will not advance until I hit the clock. Okay, there we go. The value of f of c given by the mean value theorem for integrals is called the average value of f on the interval a to b. Okay, so let's go back and review real quickly what we mean by the value f of c in the mean value theorem. Here it is. Mean value theorem, theorem 510. If f is continuous on some closed interval a to b, f is continuous on that whole interval, okay, then there has to exist some number in between a and b on that closed interval a to b such that the integral of f of x, the definite integral between a and b of f of x dx is equal to some value f of c times that length. So the mean value theorem was that, you can, let me see if I can find like this. If here's the function f in between a and b, then the integral of f between a and b, that means the area under this curve, okay? Now f has to be a continuous function like you see it is now here, okay? There has to be some value c there so that the rectangle formed by b to a to b, which is b minus a, that's the length, and f of c is the height, that this rectangle has exactly the same area as is under the curve. Has to be that way, okay? The inscribed rectangle would have less than that. The superscribed rectangle or circumscribed rectangle would be more than that. There has to be a rectangle in between at some value c. And there may be more than one value c where it'll work. If f of c, if the f function crossed, I can't get there it is, crossed several times, you could use any one of those. It's that height. That height times this width is the same area under there. Now, that f of c that we use with mean value theorem, if you divide both sides of this equation by a minus b, now the value of f of c is this area under the curve divided by the length a to b, and that gives you the average value of c. And that's why the average value theorem says that if f is integrable, if f is integrable on a closed interval a to b, then the average value of f on that interval is 1 over b minus a, in other words, the length of that area there, the length of that rectangle, is times the area under the curve. So this would be the average value. And you see you could either use this C1 here, but you're not using C1, you're using f of c, okay? And f of c is the same, where's my cursor there? It's the same here or here for this c or for that c. It doesn't matter which one you use, you're using f of c, which is this height right here. And that length, that height times this length is the average, is the total area under the curve. So therefore, dividing by the length, you get the average value of that function. That's the average value theorem. A lot of blah, blah, blah. Is that really all that useful? Well, maybe sometimes, okay? To see why the average value of f is defined this way, and this is going back in what I've been arm waving saying they're going to try to do, partition a to b into n subintervals of equal width, and that those subintervals with delta x will be b minus a over n, just like we've done before. And if ci is any point on the ith subinterval, okay, just any point in the ith subinterval, left point, right point, or any intermediate point, center point, doesn't matter, any point in that interval, then the arithmetic average, or the mean, of the function values at the ci's is, now this is the average, okay? You have n ci's, right? Alpha C1 plus alpha C2 plus alpha C3 plus alpha C4 up to alpha Cn. Those are the y values of each of those things, wherever you choose those c's to be, okay? And the average of all those, if you added all those together in equally spaced intervals, divide by n, because you have n of them, that will be your average of, or the mean of those functional values. Okay, that's just add all the scores together, divide by the number of scores you got. Okay? I don't know why I keep getting noises. I guess people are sending me emails or something, but all right. By writing the sum using a summation notation and then multiplying and then dividing by b minus a, that seems a little strange, you can write the average this way. So here's the average. It's just like we had before. Go back here. The 1 over n can come outside the summation, okay? And all you're doing is summing your f of c's, c sub I for I equal 1 to n. So that's exactly what that previous slide was, 1 over n times the summation from I is equal to 1 to n of f of c sub I, okay? It's writing what we just did in this notation. Okay, now what we're going to do, this looks strange, you multiply and divide the inside here by b minus a, which is the length of an interval. Okay? Yeah, that's your length. B from A to B, b minus a is that length. Okay? You haven't changed anything. I mean, b minus a over b minus a is 1, because b is not equal to a. You know, they're separate. Pull one of those b minus a's, the denominator one out front, and use this one over here. Well, guess what? When you put, and what they've done is drag the n back inside, move the b minus a on the outside, then this summation of I equal 1 to n of f of c sub I times b minus a over n, b minus a over n is your delta x. So this is 1 over b minus a times the sum from I equal 1 to n, f of c sub I delta x. That is your definition. As you take the limit as n goes to infinity, that, and this is a continuous function, remember, that becomes your integral from a to b of that. And that leads to exactly, well, you're not showing where it leads to. That leads to this very statement here, 1 over b minus a times that integral. Okay? Now, oh yeah, I'm sorry. I should have kept going. Finally, by taking the limit as n approaches infinity, it produces the average value of f on the interval a to b as given by the definition way up there. Well, here it is. I didn't see it down here. That gives you exactly that. When you take the limit of that sum as n goes to infinity, you get the integral, and that integral, see, the delta x became dx, the f of c sub I became f of x, and you go from a to b. I equal 1 to n, okay? I at 1 would be a, at n would be b, okay? In this figure, notice that the area of the region under the graph is equal to the area of the rectangle whose height is the average value. And that's what we said all along. Yuck! It keeps jumping. Okay, here the rectangle, if I could get it to go up, the rectangle overshoots it a little bit, undershoots it here, overshoots it big time here, but then undershoots it a little bit there. Sure enough, if you were to add these two positives and that negative, you're going to get that at least it looks like that would be about the same. So sure, that's the average value. Your f of c is that average value. Okay. Any questions on that? Now, the one big question might be, what difference does any of this make? Well, here's one. They're going to ask you to find the average value of this function, f of x is equal to 3x squared minus 2x on the interval from 1 to 4. Okay? First question, is this a continuous function? What's the answer? Anybody? Yes, because it's a polynomial function. Polynomial functions are always continuous. Okay, so we've met the criteria. How are we going to find that average value? There it is. 1 over b minus a times the integral of that function. So what's your b and what's your a? Those are the limits of your interval. So 4 minus 1 is 3. So out in front of the integral, you have a 1/3. 1 over b minus a. Then we're going to take the integral of this function here. And what's the antiderivative of 3x squared? It's pretty easy. Antiderivative of 3x squared. Anybody? Antiderivative of 3x squared. Surely somebody knows. Help me. You up this by 1. That becomes a 3. Divide by 3. That wipes out the 3 there. You just have an x cubed, right? Minus 2x. What's the antiderivative of 2x? Come on. Increase the exponent by 1. It is a 1. Increase it by 1, it becomes a 2. Divide by 2, it wipes out that 2. So that'd be x cubed minus x squared. Y'all knew that, right? Now, I don't know if I've said this recently enough, but back when I was writing things on a piece of paper and holding them up to the camera, I said, you have a piece of paper and you be working this out yourself and make sure that what I'm getting is the same thing you get. Even though now I'm going to use the whiteboard and all that kind of stuff, and we're using the PowerPoints, you still need to be working these problems. So get your piece of paper, get your pencil, and be doing these integrations. So that is the integral. The integral of this is x cubed minus x squared, evaluated from 1 to 4. So let's plug in the 4. 4 cubed is, anyone know? Please say yes. 4 cubed is 64 minus, go on. Minus 4 squared is 16. So that's 64 minus 16, I'm pretty sure is 48. Is that right? I believe it is. Minus, and then when you plug a 1 in here, you merely, and this is x cubed minus x squared, remember? That'd be 1 minus 1, that's 0. So it looks like our answer is 16. But remember you had the 1/3 out front, 1 over b minus a, so it's 16 thirds. That's what I'm hoping it is. Let's see. So here's what they did. The average value is 1 over b minus a times the integral of this f of x dx. Well, the b is 4, the a is 1, so it's 1 over 4 minus 1. That'll be a 1 over 3. The integral from 1 to 4 of x cubed minus 3x squared minus 2x dx. Okay? We've already done that. We figured this to be a 1/3, this to be an x cubed. The antiderivative of 3x squared is x cubed. Antiderivative of 2x is x squared. There's a minus in between. We're evaluating from 1 to 4. When you put in a 4 here, you get 64 minus 16, which is 48, I'm pretty sure, okay? And then when you plug a 1 in there, okay, 1 minus 1 is 0. So that gave you 48 thirds. That's the answer I got. Let's see what they got. Well, let's see, here it is. 64, 1/3, 64 minus 16, minus 1 minus 1. So looks like a 0 to me. 48 thirds. Perfect for them. Way to go. Well, what is 48 thirds? 3 will go into 48 16 times. So the average value of that function is 16. Well, this function, they've drawn the graph here. At 1, it was started at 1 here, okay, 1, 1. And then up at 4, if you plugged in that original function, 3x squared, 4 squared is 16, 3 times that is 48 minus 2x, and 4 times 2 is 8, 48 minus 8 is 40. So sure enough, these are the endpoints here, okay, and that's the curve. It is a parabola, a parabolic shape here. Let's see, did anyone else come in the class? I don't think so. Let me check. Yep, still got 15. Is that right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's right. Okay, so something between, it's a parabola there, and by the way, the origin will be at the 0, but that's beside the point. We're starting at 1 here. Okay, and just looking at the area under this curve here, that's pink here and blue there. Okay, well, the pink part is outside this rectangle, but the baby blue part, or the turquoise part, or whatever you want to call this part, is inside the rectangle. Oh, no, we don't. Okay, so that's going to be, they look like they're about the same. You can't go by looking, but at least it looks reasonable. So the average value of that function is 16. That still doesn't answer the question, where do we usually use this? Well, here's another example. Uh-oh. No, they have the example in the book, but not on the PowerPoint. So let's back off one and go to our whiteboard. And this is going to be awful, isn't it, folks? Okay. I'm going to move this as far as I can out of the way. You can't see it, but it's in my way. It's a taskbar for the whiteboard. Okay, at different altitudes in the Earth's atmosphere, this is example 5, top of page 322. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, S, as a function of x, where x is meters, or okay, the speed is in meters per second. That's the speed of sound. And the x, I'm pretty sure, is in kilometers. It's the altitude in kilometers, okay? Frankly, I would have either used y or h or something else that would indicate height. They used x, which to me usually indicates a breadth. It's all right. They can use any variable they want to, but I wouldn't have used x, okay? Now, from 0 to 11.5 kilometers up in the atmosphere, the speed of sound is negative 4x plus 341. Okay, now that's a messy thing, and I'm not sure I want to write all this down. Do just about all of you have books? Does anyone not have a book yet?
I don't.
Okay. Now, in some of my other classes, students have been sharing PDFs of the books. Does anyone have a PDF of the book? Isn't that what you get through, what is it, Cengage Unlimited? Yeah, I think that's what it's called. Do you have a PDF of the book, people? Called an ebook? Now, it didn't quite seem legal to me, but students have been sharing those, even though that second student may not have bought it. But one of the students in yesterday's class said, hey, because of the COVID-19 and stuff like this, they're letting people do this. I don't know if that's true or not, but if someone can send her, Morgan, maybe you don't need the whole book, but maybe just the chapters we're going to be doing, 5, 6, 7, blah, 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 whatever chapters we're going to be doing, if you could just send them that, then you'll have a book to look at. Is anyone willing to do that, or do you feel like that is, the students in yesterday's class said, yep, nope, they're letting people do this. I don't know. I was hesitant, but that's what the student said yesterday. So if you can get a copy, an ebook, you can at least look at this. What I'll do now is hold this up and let you see what we've got going here. Okay? Now you probably can't hear me as well because I'm behind the book. Okay? But there's your function. S as a function of altitude, where x is in kilometers, s is in meters per second. That's your speed of sound. Okay? Now, here's the graph of that. Okay? As you go from, so sound senses slow down for that first, whatever, 11 and a half kilometers that you go up into the atmosphere. Then it sort of levels off for a while, then gradually goes back up, goes up a little faster, and then drops off again. That's what this piecewise defined function is telling you. Okay? Now, whoa, I just lost the page. Okay, now, tired of holding it. So that's what we're looking at. So what are we doing here if we're saying, the question is, what is the average speed of sound over that entire interval from ground level to 80 kilometers up there? Okay? So what you're going to have to do here, now the good news here, every one of these functions is linear. That 295 from 11.5 to 22 kilometers, that's a constant function, okay? So you could calculate the area under each of those blocks, you know, different B minus A's and different, you know, altitudes, and you could do it. It's a fairly simple process. Not super simple, but it's not as bad as it could be. And that's what they do at the bottom, but there is way more writing there than I want to do on a screen. Okay? So what they do is add up each of those areas. Okay? The first one for the first 11.5 kilometers is 3657. Now that doesn't make a lot of sense. That's the total of your speed of sound times the interval, okay? And then the next is 3097.5, then a 2987.5, then a 5688, and then finally a big long 9210, and you add all those up together and then divide by 80. And because that's your interval, 0 to 80, the whole interval, and you come up about 308 meters per second. Whereas at the surface of the Earth, it's right around 341 meters per second. So it's a little bit, the average speed goes down as you go up. Not always, I mean, but there's certain things where it dips and then goes up and dips again. Okay. That's way too much writing on a whiteboard, so I'm not about to tackle that. Okay. But if someone can share that with Morgan or anyone else who doesn't have a book, then that would be good. Now, if you have your own book, see if you can find any example of average value of a function and do that one. You don't have to do this one. This is nothing special about this. It's just the one this book shows. And by the way, it has one of the coolest pictures. I've seen it many different places, usually in physics books. You know what that's a picture of? That's not an artist rendition. That is an actual photograph. Anyone know what it is a photograph of? Someone breaking the sound barrier. If you think about what is sound, sound is a pressure wave. Hold your hand in front of your mouth while you're speaking. You can feel little pulses of pressure. Okay? So sound is a pressure wave. That's how you can hear, because your ear, the eardrum, and all the other intricate things in there, we're wonderfully made here. They are vibrating just ever so slightly, amplified by all the other stuff in your ear, and your brain is interpreting that and understanding it. We are an incredible machine, okay? Now, so sound is a pressure wave. It goes at a fixed speed. And whatever this one was, it's probably somewhere up there, I'm guessing around 330 meters per second. I'm just making a guess, so around 330 meters per second, okay? I just picked something out of that first group there, okay? And that's where the plane is going. Now, this is a jet plane that can travel faster than 330 meters per second. So what's happening as it's traveling and picking up speed, the sound waves that are coming from the plane are actually getting compressed because the plane is traveling almost at the speed of sound, and as it compresses them, all the things that are in the air, little droplets of moisture and other things like this, on a humid day like that, that would be a really big cloud, okay? They are getting compressed, and then when the plane exceeds the speed of sound, it goes through that compressed droplets. In weather, they call it nuclei. Let's see. Have a nucleo something and others. Little units of moisture. That's what that is. That plane is breaking the speed of sound, and that photograph caught it just as it's going. They mention here Charles Yeager was the first person to fly at the speed of greater than the speed of sound, and for a while they thought everything would fall apart, but it didn't. So he made it. So I'm sorry, I opened the whiteboard and then decided not to write a thing on it, just because that problem has way, way, way too much writing than I was willing to tackle. Okay, so let's go back to, and now why do we have to, okay. Wait. All right, here we are. Second fundamental theorem of calculus. This is on page 323. Let me get the book down in front of me. All right. Remember what the first one was? Basically, the first one tells you how to do definite integrals. That's what the first one does. Here's what the second one does. Earlier you saw the definite integral of f on the interval from a to b was defined using a constant b as the upper limit of the integration, and x is the variable of integration. However, a slightly different situation may arise in which the variable x is used as the upper limit of the integration, a still the lower limit, but x now replaces b. And now what you have now, if you think about it, that would be as x increases from a to somewhere beyond a, as x increases, you're doing areas under different portions of the curve. Whatever that curve's doing, you're looking at the area as a function of how far you are from A. That's what you're doing. To avoid the confusion of using x in two different ways, they usually substitute, and remember the independent variable in an integration is a dummy variable, especially in definite integrals. So they temporarily use t as the variable of integration, because definite integral is not a function of the variable of integration, because that's what you're getting rid of when you evaluate it. So you can use any letter you want to there. Just don't use x again. Use t, s, stickman, whatever you want to use. Okay? So here's the definite integral as a number. This is the first fundamental theorem of calculus. Says that if you have a fixed interval, constant function, and you integrate that, this gives you the area under that, and that area is a fixed value. It's a number, okay? The integral from a to b, those are all constants. F of x dx, this is a variable function, but you're integrating that over your dx's and then evaluating between those two, and that comes up with just a number. You don't have a plus c anymore. You don't have x's in there anymore. You plug in the b and the c when you do the integration, and the x's disappear. So if you're doing that same, let's call it the area under the curve f, and look at what they use. Our good old favorite capital F, which we used to use in antiderivatives. Remember, and that's basically what it is. The antiderivative of f, capital F, antiderivative of little f, that is, you evaluate the integral from a to x now of f of t dt. And basically what is this doing? That is, the antiderivative of f of t is capital F of t, but then you're evaluating that at first at x and then subtracting off at a. So this is your variable x, This is just a dummy variable, okay? And your capital F is now a function of little f. Now you might say to yourself, what about that capital F of A? There's your constant of integration, because this is no longer a definite integral. Okay, so here's example 6, bottom part of page 323. Evaluate this function, capital F of x, and it's equal to the integral from, oh, here comes Anita. She must have had to leave and come back again. So I think we'll still be at 15 people, right? Yeah, we'll still be at 15, I guess. Did anyone else come in since I originally called roll? Specifically, is Houston here? Lal here? James Mullins here? Or Jesus here? Or Angelica? Those are the ones that I'm not seeing so far today. Okay, so I assume we got the ones we started with. Okay, so we're calculating this antiderivative function, though we're not calling that anymore, is the antiderivative from 0 to x of cosine t dt. What's the antiderivative of cosine t? Anyone help me? Anybody?
Negative sine t?
That not negative, positive.
Oh, sorry.
Yeah, the derivative of cosine is negative sine. The antiderivative of cosine is sine. Why? Because the derivative of sine is cosine. Okay, so that's sine t. So you're going to have, this will be evaluated from 0 to x. That'd be sine x minus sine 0. Guess what sine of 0 is? 0. Okay, so let's first evaluate this when x equals 0. Well, guess what? You can do that in your head. You're going from 0 to 0, which is 0 width. So that's going to be 0. I can do that one, okay? Now pi 6. What's the sine of pi 6? Anyone remember? Please say yes. Sine of pi 6? 1/2. Pi fourths, sine of pi fourths. Anyone remember that one? Oh, I got to talk with your trig teachers. It is square root of 2 over 2. Sine of pi thirds. Please say you remember that one. Okay. Square root of 3 over 2. And how about pi halves? Everybody knows that, don't they? What's sine of pi halves? Sorry, I've got a scratch in my throat. And that is water, people. Okay. Sine of pi halves is 1. Okay. Hey, did y'all not ever learn the easy way of doing this? I didn't when I was in school either. I've picked it up in a book since then. Okay. These are our favorite angles in radian measures. Okay. And when you're doing the sine, it's square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Well, square root of 0 is 0, so that's 0. Square root of 1 is 1, so that's 1/2. Square root of 2 is square root of 2, so that's square root of 2 over 2, square root of 3 over 2, and square root of 4 is 2. 2 over 2 is 1. Okay? That's a real simple way to remember those are our favorite functions. So I think we've just done the problem. Let's see how they did it. Well, they're not going to let me advance until I click the screen. Okay? All right. You could evaluate 5 different definite integrals if you wanted to, or you could just do it once and make it such simpler to fix the x as a constant temporarily to obtain the integral from 0 to x of cosine t dt would be sine t, antiderivative of cosine t is sine t, evaluated from x is 0, and when you do that, you get sine x minus sine 0, which is what we did, sine of 0 being 0, then, so this equals, sorry about that, sine x, okay? All right. And then you just go in and plug in these values. When x equals 0, it's 0. Yeah, well then you have an infinitely thin rectangle. And sine of pi 6 is 1/2 root 2 over 2, root 3 over 2, and 1. Okay? And this is showing what you're doing there. You're letting the area be a function of t, which is now taking over as your horizontal axis, whereas the vertical is still y. When x equals 0, you don't have a rectangle at all. The area is 0. When it's pi 6, then this f of this is 1/2 root 2 over 2 here. Oops, here comes somebody. I don't know who it is. Was that Cal? No, it's someone new. Who just came into class? This thing blocked my view and I couldn't see it. Who was it just came in? Did any catch a name? I'm guessing Houston, Lal, James, Jesus, or Angelica. Who was it came in? Help me somebody. Did you see them? Anybody? Who just came in the class? Oh, let me try. Yes.
This is Houston.
Houston, excellent. Glad to have you. Okay. I saw that someone was coming in, but you know this box that shows up in the middle of the screen there? It was blocking you. And I guess, I don't know why it's there. It's a stupid thing that Zoom does. Here's my assumption. It's protecting your identity, I guess. Though I'm calling roll, but you see, Zoom isn't always for classes. Okay, so now, ever since that happened, it's going to be showing up periodically here. I don't know if you can see the rectangle or not. You can't see what's behind it, but right now nothing's behind it. So this is example 6, the solution of 6. Okay, now this does have another name, and I think that's what the next slide's going to go. This is sometimes called an accumulation function. So you start here with nothing under that curve, then a little bit, 1/2, a little bit more, root 2 over 2, that's 0.7 or approximately, root 3 over 2, that's 0.87, and then here it's up to 1. So that's your accumulation function. Not just for our favorite little values there, but any value x that you put in there. You can think of the function f of x as accumulating the area as you go from t equals 0 to t equal x. Okay? For x equals 0, certainly the area is 0 because f of 0 is 0. For pi halves, it's all the way out to 1. Okay? That gives the accumulated area under the cosine curve for the entire interval 0 to pi halves. Not just our favorite little angles, any angle. That interpretation of an integral as an accumulation function is often used in applications of integration. Okay? That's coming up later. Okay. Any questions on this? All right. I think we're flipping to page 324 now. Yeah, top of 324 if you got this book. In example 6, note that the derivative of f is the original integrand with only the variable changed. That's the capital F, okay? So the derivative of f of x was sine x, remember. Derivative of that with respect to x is cosine x, and if you plug that back in here, you get that. That's how we always check our antiderivatives. Take a derivative, see if you get it. But that result can be generalized in the following theorem, which is called the second fundamental theorem of calculus. If little f is continuous on some open interval I, now this box may be blocking some of that, but that says I, containing A, my cursor went away, containing A, then for every x in that interval, the derivative of an integral is simply this function, f of x, f of t, evaluated at x. That's what it is. That's how far along that accumulation you've been. If you take the derivative of an integral, you undo it, and you wind up with the function that was inside, evaluated at that value of x. Doesn't matter what the a is. It didn't have to be a 0 that produced a 0. When you took the sign of 0, it became 0. It doesn't matter. It's your f of x. Okay. Any questions? Let's see how we're going to use this. Use the area model. Okay, let me make sure we've got there. Yeah, there's second derivative. They have the proof of that in the book, and you certainly are welcome to look at that. I'm trying to find where this slide picks up here. I don't see it, okay? Oh, here it is, yeah. It's the bottom of page 324. That's where this one picks up, after the proof. Using the area model for different definite integrals, the approximation f of x dx, delta x, f of x times delta x is approximately the integral from x to x plus delta x of f of t dt. Now, where in the world did that come from? Well, if you think about that, you're only changing your interval a little bit. As long as delta x is very small, you're only changing a little bit here, okay? And if the average value of this function, remember how we did that? We did 1 over b minus a here. Remember, n over b minus a was your delta x. So basically, if the delta x is your this b minus that a, that is indeed delta x. Multiply that here, and you have the product of these two is approximately equal to the integral under that. Can be viewed as saying that the area of a rectangle of height f of x, that's what I was just trying to say, that would be your average value, you might say, and width delta x, that's your b minus a, in this case, where that's your b, that's your a, subtract this from each other, the x's go out, that just leaves you delta x, is approximately equal to the area of the region lying between the graph of f and the x-axis on that interval. Now, as soon as this little rectangle fades out, which I hope it will soon, fade out rectangle, okay, there it goes, it's beginning to go now. If this is your function here, and you're going from x to x plus delta x, so this width here is your delta x, then f times delta x, the area under here, is fairly close to being what the area is under the curve. Sure, there's some error. In this case, it would be a positive error. Over here, it would have been a negative error, okay? But it's fairly close, as long as it's not doing anything super dramatic, okay? Now, you can't see this, but or I can't see it. You may be able to. F of x is equal to, well, I can't, that thing gets in the way. That's that same function we have up here, okay? So, anyway, any questions on this? Again, you might say, so what? I mean, it seems like they're giving us all these different forms. Well, let's see if we can use that or apply it in example 7, okay? And this is in the book. What are we doing here? Taking the derivative of an integral, and the integral is evaluated from 0 to x. Now, it doesn't matter what this bottom one is. It does not matter as long as that's a constant. How do you undo a derivative? Okay, the derivative undoes the integral, and it leaves you the square root of t squared plus 1. Only you plug in the x instead. The answer is simply the square root of x squared plus 1. That's the answer. I wish I could make it harder. I haven't figured out how. When a derivative undoes an integral, you just take the variable here, plug it in there. Okay? Note that f of t is the square root of t squared plus 1, continuous over the entire real number line. okay, because this is always positive, so that's continuous everywhere, okay, for any value of t, positive t and negative t. Now, if you were to graph that, it's a weird looking function. Let me sort of draw. It comes up like this, and it goes like this. So it's kind of like a butterfly or a bat's wings or something like that. It has a cusp there at t equal -1, I guess it is. No, that's not quite right either. Doesn't have a very sharp cut. But anyway, it's continuous. May not be differentiable, but it is continuous. You don't have to worry about that now. But it's continuous everywhere, so all you have to do is the derivative undoes the integral, plug the variable here of integration in there. And that gives us, using the second fundamental theorem of calculus, the d by dx of the integral of 0 to x of that is simply take this argument here, the integrand here, plug in that value for x, square root of x squared plus 1, before it fades out. Okay, that looks pretty straightforward, but I'm sure they can make it more complicated. And I bet you example 8 does. They usually show you the simple examples, and then the harder example you have to fiddle with. Okay, so let's fiddle. This time I think we will use the whiteboard. Okay, this doesn't have umpteen million pieces to it. It's just pretty straightforward. Find the derivative of f of x, where your capital F of x is equal to the integral from pi halves down here to x up here. No, I'm sorry, to x cubed up there. If I can read, it's really a small print there. Is that what it says in your book, x cubed? Now this doesn't quite look like what we were doing before, Houston, or Dorothy, or whoever it is. You're not in Kansas anymore. Cosine t dt, that's the argument here. Cosine t dt. Painstaking, isn't it? Okay. Or painful, whichever. Okay. Now, what we're supposed to do is take d by dx of this thing. It says find the derivative of this thing here. So we're going to do a d by dx of it. However, this isn't an x here. This is an x cubed here. So we're going to do something. It's called a substitution. We're going to let u equal x cubed. Right? Now that would be a u here, okay? But the problem is this is a function of f. So to take derivative of this with respect to x, you have to first take derivative of f with respect to u and then take derivative of u with respect to x. Whoops, that's pretty ugly. Okay. And what would this give you? This would be df dx, right? Because these sort of like they cancel out. Don't say that to a mathematician, but that's what it looks like. This would be your df dx, okay? Well, let's do what it said here. Derivative of that would be, ooh, this is ugly, I guess we can leave this as pi halves. It really doesn't matter because it doesn't matter what that is. T's going from pi halves to u now. Okay? And then this would still be cosine t oops, that's ugly, isn't it? Okay. Now, I left something out. This is a d by dx. We did a d by dx of f here. We need to do a d by dx here too. D by dx out in front. I can't write. That's supposed to be a dx. I didn't leave enough room and it's really ugly. Okay. We did d by dx of f here, doing a d by dx of this here. Okay. Except we have a u. Okay. Well, we know what this is with respect to u. I'm sorry I messed this up. Let me, I hate to do this because it was so painful to do the first time. Okay, let me erase this because it just got really messy. Okay, I needed to allow more room. Okay, now let's go back here again. Okay, now what we did was a d, we took a derivative of this, it's d f dx, but because we're introducing this u in here, we had to do it in two parts, df du dx. But we also have to do that here too. We're taking derivative of this with respect to x, you take derivative of this side with respect to x. So that's a d, whoa, that's ugly, by dx, well, I'm sorry, du of this thing, I think so. Why couldn't they have just said this a 1 down here or something, not a pi halves? That's such a pain to write. And we're going to do this with respect to u, and then cosine t dt. Yeah, this is hard. It's not really that hard, it's just painstaking. Okay. But we still need a du dx here because this was df du, that's what this is, and then we need a du dx out here. Yuck. Okay, and again, we made this a u, that's what we did here, and then we took the df du, and that's this part here, d by du of that, and then this is the part out here, okay? So this is the f as a function of u, and this we can do. Second fundamental theorem of calculus says when you take a derivative with respect to that variable of the integral of this thing, you merely get cosine u. You just plug this variable in there. Then you got to do a du dx. Well, someone tell me what du dx is. Can you do that? I'm just going to call it u prime because I didn't leave enough room to do du dx. What will u prime be? You can tell me, can't you? Take the derivative of x cubed. We've been doing integrals so long, you find how to take a derivative? 3x squared. D by dx of u would be 3x squared. Okay? So then this part here would be a 3x squared. Okay? Well, what's cosine of u? Well, u is x cubed. So our final answer is cosine of x cubed, because that's what u is, times 3x squared. So I think I'm going to put the 3x squared out front, because otherwise it'll get confusing and you think that's part of the argument. It's not. Move that out front, and there's your answer. Okay? Cosine x cubed, they put it afterwards, they put it in parentheses, times 3x squared. I like to write it in front, and you don't have to have the parentheses there. And since I'm writing with my finger on a keypad, that's a lot easier to do. Okay? Now, if you wanted to do this the other way, you could have done it. Okay? You could have done the antiderivative of this. Anyone tell me what the antiderivative of cosine t is? Please, somebody. We just did it earlier. I'll put you all to sleep, huh? Sine t. Evaluate from x cubed to pi halves. Well, excuse me. Sine of x cubed minus sine of pi halves. Well, sine of pi halves is 1. We did that earlier too. So you get sine of x cubed minus 1, okay? And then, so that's your derivative of this with respect to, well, okay, you evaluated this, okay? And then what you're doing is taking the derivative of that. And what's the derivative of sine of x cubed plus minus 1, okay? Well, sine of x cubed is cosine of x cubed times, chain rule, 3x squared, and then the sine of 1 is 0, or minus 1 is 0. So there, sure enough, you get the same answer that way. Okay? Now, if you look in your book, they may describe it a little bit better, but boy, writing with my finger on the keypad is not fun. All right. So I think we can go back to our PowerPoints. Are there any questions on this before we leave it? All right, so let's go back to our PowerPoints, 5.4. And this is so aggravating. Okay. Oh, it went back to the right place. Okay. So let's move on to net change theorem. The net change theorem. Putting theorems on top of theorems on top of theorems. Okay? The fundamental theorem of calculus states that if f is continuous on some closed interval from a to b, then the antiderivative of that, the capital F, is an antiderivative of f on a to b. That's what I was just saying, calling it. So this would be this is the first fundamental theorem of calculus. The integral from a to b of little f of x dx is capital F evaluated first at a and at b, and then subtract from it the evaluation at a. Now, because f prime, capital F prime, is little f, that's from the second fundamental theorem of calculus, that statement can be written this way: the integral from a to b of f prime of x dx is simply f of b, capital F of b minus capital F of a. That's the same thing here. This is the same thing here. Now, this quantity here represents the net change of f on that interval, a to b. The net change of f on that interval, a to b. All right? That's what the combination of first and second fundamental theorems of calculus tell you. Okay? So here's how we state that. Theorem 512. If f prime, capital F prime, is the rate of change of a quantity, capital F, which was your antiderivative, then the definite integral of that f prime from a to b gives the total change, and then they call that the net change. And they don't sound like they're the same meanings, but they are, okay, of f on the interval from a to b. So the integral from a to b of f prime of x dx is simply capital F of B minus capital F of A. Was there a question? Okay. I keep hearing things, but I can't tell if it's someone talking to me or just the microphone popping in and out. All right, so let's move to example 9. A chemical flows into a storage tank at the rate of 180 plus 3T liters per minute, where T is the time in minutes, and it's going from 0 to 60 minutes over a 1 hour period. Now, what does that mean? That means at the beginning of that hour, when T is equal to 0, the flow rate was 180 liters a minute. At the end of that hour period, where 3 times 60 is 180, it's now doubled the flow rate. So the flow rate was slowly increasing over the entire time of that hour, okay? Until at the end of the hour, it's going twice as fast as it was. So it says, find the amount of the chemical that flows into the tank during the first 20 minutes, okay? Not during the hour, but during the 20 minutes, okay? Well, that sounds like, okay, let me give you a few hints here. When you see rate, think derivative with respect to time. And since the T is representing minutes, okay, this is a rate with respect to time. So this right here, when they say a rate of this, this is some df dt. The rate is df. How much is f changing over time? And this is your formula for it. So that is your, you could call it capital F if you wanted to. So this is your capital F prime, okay? Now, it says find the amount of chemical that flows into the tank during the first 20 minutes. So it sounds like to me, oh, I can't write on this screen. I was starting to write. Let me just try. I don't think it'll let me. No, I know it won't let me. Okay. No, it'll just mess up. Okay. So let's think through that. The integral here then would be the integral from 0 to 20 of this f prime here. And we just found out what the answer is f at 20 minus f at 0. Okay, so f at 20, this thing right here would be 180 plus 60, that would be 240 minus 180. So it looks like about 60, if I'm doing it right in my head, liters. Okay, let's see how they did it. Let C be the amount of chemical in the tank at time t. Okay, don't know why they introduced that, but that'll be fine. C is a function of t. Okay, then C prime represents the rate at which the chemical flows into the tank. Okay, I'm sorry, I had it flowing out, but flowing into the storage tank. Okay, so this is the C of t is the amount of chemical. I was using capital F, they're using little c. I guess C standing for chemicals. So the rate at which it was going out is this thing right here. That's your 180 plus T. So that is in the first 20 minutes, the amount of flow out would be this integral here, and this would be C prime, and the C prime is the rate at which it was flowing out. And now, what you could do, okay, is, yeah, you can do it this way, 180t minus, and then the antiderivative of 180 is 180t, of 3t would be 3t squared over 2, so it's 3 halves t squared, evaluated from 0 to 20. So at 20, this would be 360 plus 20 squared would be 400. Half of that would be 200. 3 times 200 is 600 plus 360, 960 I think it is. No, what was I doing? 36, I'm sorry, I left off a 0. 3,600 plus 600, 4,200. So in the amount of chemical that flows into the tank during the first 20 minutes, I was way off. 4,200 liters. Okay. Now, another way to illustrate the net change theorem. So frankly, that was just an integration. Okay, that was all it was. You just put this as your integran and then go for it. I don't see how they really used this. Oh yeah, I'm sorry. You did the antiderivative of this. We weren't ever given what the f of b was. Okay, that's right. Okay. Sorry, I got crossed up. Okay. So that's exactly what we did, and it certainly works. Okay. Another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line where s of t is the position at time t. Then its velocity, v of t, is s prime of t. Yeah, velocity is first derivative of its displacement, okay? And it's moving on a straight line, so that's pretty straightforward, okay? So the the integral from a to b of v of t would then be simply s of t, s of b minus s of a, because the antiderivative of v of t is s of t, okay? And that definite integral represents the net change in position or displacement. Well, of course it does, okay? Velocity of a particle moving along a straight line where s of t is the position at any time t. The velocity is that. So if you integrate its velocity over time, if this is the slope and you're integrating that over time, the change of velocity will then be the total net change of displacement of the particle. Wait till you get to physics and you'll see that come to life a little bit better. Okay, let me make sure we're not skipping an example here. No, we aren't. We're getting there. Okay. When calculating the total distance, now not net distance, okay, the total distance traveled by a particle, you must consider the intervals where v of t is negative and the intervals where the v of t is positive. If you're doing total distance traveled by a particle, okay, and you'll see this in physics too. When v of t is negative, the particle moves to the left. Well, if you're interested in total distance, you got to count that distance it traveled there and back again, or wherever it's traveling, you have to do the total distance. The net distance is wherever it started from to wherever it ended. That's it, okay? But the total distance, you have to take into account how far it went this way and back again, or wherever, okay? It's sort of like this. Remember, this example maybe, if you're running around a track, okay, that's a closed loop. If you start here, run all the way around the track and start here, what's your net distance you moved? You didn't move at all. You started at the same place you ended. What's the total distance you moved? You have to calculate the whole circumference of the track, or the distance around the track. So that's sort of what they're talking about here. When v of t is less than 0, it moves to the left, and right, v of t is greater than 0, the particle moves to the right. Calculate the total distance traveled, you integrate the absolute value of the velocity, and you have to break it into different intervals. Okay? So the displacement of the particle is simply the integral of that velocity. The total displacement, the net displacement, okay? And that would be now where are they getting these capital A's? Okay, yeah, okay, I got it. Yeah. Oh, here we go, down here. The net displacement, if you started here, okay? Okay, now this is the velocity curve, not a displacement curve. You started here and you're moving in a positive direction, fast here, but now slowing down here, but still moving in a positive direction. Now you stop here, that's where the velocity is 0, and now you move backwards here, and then you come back and stop again, and start moving ahead again. So your total displacement, the area here would be how far you moved to the right. This then is how far you moved to the left, so you subtract that off, and then you come back here, and then how far you move to the right again. That would be your displacement. You started here, you went here, you backed up here, and then you went here. Total displacement was where you started to where you ended, okay? That's displacement. The total distance traveled, though, is the distance you travel from here to here, then the distance you travel from there back to there, and then the distance you travel from here to here. You're traveling the whole time, so you do the absolute value of this one here, which gives you a plus A. So the total distance traveled would be the sum of all those distances. Even the ones that were negative, you take that, you don't subtract it off, you add it. Okay. So here's example 10, and this is in the book. The velocity in feet per second of a particle moving along a line is, strange one, t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. Now the first question is the easy one, believe it or not. What is the displacement of the particle on the time interval 1 to 5? Well, the v is equal to ds dt, and if you did the dt times this, integrate ds, and integrate this, you get the total distance traveled, the total displacement. So that's just your straight integral. What's the antiderivative of t cubed? Anybody? Please, somebody. What's the antiderivative of t cubed? T4 over 4 minus 10 t cubed over 3 plus 29t squared over 2 minus 20t. Okay? That's your antiderivative. Okay? Evaluate that from 1 to 5. Can I do that in my head? Probably not. Okay? Pull out a calculator. I think I've got one here. Whether I get all the numbers right, that's a different story. But let's try it. This is my phone, so it's not going to be quite as easy as a calculator. Okay. So what did I say that first one was? T fourth over 4. So you're raising 5. Oops, I got to turn my phone sideways so I can do this. That would be 5 raised to the 4th power, so that's the y to the x key on this one, minus 10 divided by 3 times t cubed. I know what t cubed is, I think. 125, isn't it? 5 cubed is 125. I think I knew the other one too. I hadn't thought about 125 plus 29 over 2 times 25 minus 20 equal, I got about 551. Now I don't know if that's right or not. Oh, they ew. That's way too big. I did something wrong there. Probably punching the calculator. Let me go back and do that in my head. 5 to the 4th power. 25 times 25 is 625, I think. Okay, let me go back and do that. Okay, let's clear that. So I may have forgotten to divide by 4. I think that's why I did it. It's 625 divided. Okay, 625 divided by 4 minus, yeah, I forgot to divide that first one by 4. 10 divided by 3 times 125 plus 29 divided by 2 times 25 minus 20 times 5 is 100. I forgot to do that too. Okay? And now I got a way too small of a number. 32 divided by 2 is just a little bit more than 10. So I'm punching something wrong on the calculator, but you get the general idea. I'm not going to do it again. It's not that hard to do. Write it down. Please write it down. Okay? So that came out being 32 thirds feet to the right, which would be just over 10 feet to the right. I got 2.08. I did something wrong. But anyway. All right. Now, what is the total distance traveled by the particle? This is the harder part. Okay? What we have to do first is figure out where our zeros are. Okay? So we've got to take this function here and see if there's any way we can find the zero of that function. Okay? Now, if you remember back from pre-calculus algebra, how you find the zero of the function, one way is your rational zeros test. That rational zeros test is going to be all the possible factors of 20 divided by all the possible factors of 1. We're only interested in those between 1 and 5. So the factors are 1, 5, 1, 2, 4, and 5. Those are potential answers. So let's calculate each one of those. Okay? Well, let's do it at 1's the end point, and that happens to be a 0, and we don't really care about that one, but let's do it. Let's just show it. That would be 1 plus 29 is 30, minus 10 minus 20 is minus 30. Yep, that's a 0. But that's your end point. That doesn't matter. Okay? Another possibility would be 2. Let's see what happens when we put a 2 in there. Okay? 2 cubed is 8. Okay? Minus 40 plus 58 minus 20. Now I got 6. I've got big fingers on a little screen. Did y'all get that too? Did anyone do that with me? Let me try it again. 8 minus 40 plus 58 minus 20. Yep, 6. Okay. So that's not a 0. Don't sweat that one. Okay. 3 won't go into 20. 4 will go into 20. Let's try 4. 4 cubed is 64 minus 4 squared is 16 times 10 is 160 plus 4 times 29. Let's just do that. 4 times 29. I don't want to do that one in my head. I could, but I don't want to. Minus 20. And that is a 0. So t equal 4 is a 0. Let's see if t equal 5 is a 0. I think I can go back to my calculator like this because you can do all these. 5 cubed is 125 minus 250 plus 5 times 29 minus 20. And there's another 0. So 4 is a 0, 5 is a 0. Okay? And those are the, oh, well, 5 is your endpoint. Who cares? So 4 is your only 0 in the middle of it. Okay? So here's what we've got to do. We need to find out where is that negative. My guess is negative. Well, we already did it. We already figured that out. Because remember when I tried 2, it came out a positive value. So if it's 2 is positive from 0 to 4, then it's negative after 4. So we've got it done. So now we do our integral. Okay, the first integral will be from 1 to 4. And we do this integrand. Okay, and then we do a minus, okay, the integral, or you can do it any way you want to do it. Because you're going in a negative direction, then you do minus the integral from 4 to 5 of this thing here. Because you know that's going to be a negative number, and a minus that number is going to make it positive. Okay? Now, I'm not going to try that in my head. I've tried that too many times, or even on the calculator. It's too many opportunities for mistakes. So let's watch and see how they do it. So here's the first one. Okay? All right. The first one here, the displacement is just the integral from 1 to 5. And just like we said before, that's going to be the integral from, you know what I forgot to do before? I forgot to subtract to 1, I think. I don't know. Anyway, here's your integral. T fourth over 4 minus T 10 over 3 T cubed plus 29 over 2 T squared minus 20T. Evaluate that from 5 to 1. And I think I forgot to subtract off the 1. That's where I made the error before. Sorry about that. Okay? That would have given it to me. So you plug in the numbers, and now would be a good time to do that. And, well, you can do that. You can plug in the numbers, okay? And you got a 25 over 12, which is exactly what I got. That was the 2.08 something another. That's what I got. I forgot to subtract off at 1. I was subtracting off at 0. But that's a negative number there. When you do 1/4 minus 10 thirds plus 29 halves minus 20. That gives you a negative number. So that gives you a negative number here, but minus a minus gives you a plus. And that's where you get 128 over 12, which reduces to 32 thirds. That was my dumb mistake. I forgot to subtract off the lower limit where it was 1. I was thinking it was 0. It wasn't. Okay. Now for the second part, so the particle moves a little over 10 feet to the right. That's the total displacement. It counts where it started, moved to the right for a while, then moved to the left and ended about 10 feet where it started. Well, why did it do that? I think my Zoom is screwing up. It did this once yesterday. Can y'all hear me? Someone say something, please. Can you hear me? Yes or no? I think it just disconnected us, and I don't know why. I'm going to stop this. I don't know what it's doing. And we're going to start it again. So y'all are going to have to come back in the class. Sorry about that. Can you make your way back in? I don't know if my signal's bad. I don't know what's going on here. I'm having trouble connecting. Now, where it did it yesterday was when I was trying to schedule it. It did this kind of stupid mess. I don't know if here's my problem. Right here. No internet access. So I'm going to have to leave the meeting. Okay. I don't know why my internet just ended. Got excellent signal strength. Okay. We're connected. We've got excellent signal strength, but I have no internet. So I think what I have to do is shut down. Yuck. Okay. All right. Still recording, but there's nothing really to record now. I'm going to pause the recording for just a few minutes until I'm beginning the thing again. Now, how many people do we have here? We're down to 10 people now. Hopefully the others will be coming back. Okay. Okay, here we go. Anita's coming back. Were y'all there the whole time and just sitting there waiting for me to show back up? Excellent. Thank you for doing that. I don't know why. I don't know if you can see my screen here. Can you see my little indicator here on my internet access? You might not be able to see that where the arrow, my cursor is going around and around. No, you can't see it. Okay. Okay. It was a great signal, but no internet. Okay. And I don't know why. So what I did, I changed to a different provider and I got it back. But it took a while even for that to happen. So let's go back to where we were. Wait, that's not what I want. Let me go back to my share screen here. 5.4. Okay. Well, I'm trying to go to the current slide and there we go. All right, let me get this box out of the way. It's a toolbar. Now I've got another issue. I don't see my internet signal anymore. So if I go out again, I guess it'll show up just like this one. Okay. Now, where we were before, we figured out the particle moved as a total displacement only a little over 10 feet to the right. Started moving to the, okay, here's Jonah coming back. Welcome back, Jonah. I don't know where you went. No, I'm just kidding. My internet went out. I don't know why. I had a great signal, but it went out. Okay. So, we had already done this part. Well, I can't get it to advance and still I click on the slide. This is the craziest thing. Okay. All right, I guess we were still talking on this one. So what we have to do now is the total distance, the B part, you have to figure out how far it went to the right, that's from 0 to 4, and then how far it went to the left to go from 4 to 5 seconds. We know that it stopped 10 feet from, 10 feet from where we started, a little over 10 feet from where we started, but it went past that and came back to that again. So we've got to add this part in here. So what we break this down into two intervals, okay? To find the total distance traveled, you calculate the integral from 1 to 5 of the absolute value of the velocity. And that's why we started off doing where did the velocity change direction? And that's where our 0 was at 4 seconds. Okay. Now they're going to do the same thing here, and you see the same thing we did. They drew a graph. Well, we calculated and knew it started at 0 here, and we tested at 2, and it was up around 6, I believe it was, at 2. And then it kept on climbing, and then it went down to 0 at 4, and then it happened to go back to 0 at 5, but who cares? That was the end point. So it was a positive velocity for this portion, a negative velocity for that portion. So we calculate the integral of your velocity from 1 to 4, and then subtract from that the integral, that same integral from 4 to 5. Now, you could say add the opposite of it, which is the same as subtracting, okay? So that's exactly what we're going to be doing here, okay? And they started off by saying the fact that v of t can be factored as t minus 1, we knew that, t minus 4, we knew that, and t minus 5. We knew those were the only one. The only other possible one in there was at 2, and 2 would not give you a 0. So we found that information too, okay? So what we do here is the integral. This is exactly like I said, from 1 to 4 when you're going in the positive direction, and then subtract from that the integral when you're going in the negative direction, because you know this is going to come out a negative number. The minus will make a plus. Okay, we've already done the antiderivative. That's the same. The difference is your limits here. Okay, so again, this is t fourth over 4 minus 10 over 3 t cubed plus 29 over 2 t squared minus 20t. It's going to be the same things here, except everything's going to have a minus sign in front of it, okay? And these are evaluated from 1 to 4, and these are evaluated from 4 to 5. Okay, so this is where you pull out your calculator again. This time you're only going from 1 to 4. We've already calculated the 1. We'll go back and do it again. But we plug in the 4 here. Okay? And I don't guess it's worthwhile me plugging in the calculator. Let's just see what they get. You can plug in a calculator. That gives you 45 fourths for here. That would be, I think that's 128 over 4. Wait, let me think. Yeah, 128 over 4 minus 10 thirds times 64 plus 29 halves times 16 minus 80. Okay, that should give you 45 fourths. Then you subtract from that. Okay, don't forget the 1 I did last time. Subtract 1/4, 10 thirds, a minus, so you're adding 10 thirds, minus the 29 halves, plus the 20. So that gives you the 45 fourths. I'm sorry, I just did it as if the 4 was. When you subtract the 1, this evaluated at 1, that gives you that. Then you have a minus, and then you have, we did this before, 625 over 4 minus 10 thirds times 125 plus 29 halves times 25 minus 100. But that's, you could negate that to begin with, or just keep the minus sign out there. If you keep the minus sign out there, then this would be a minus. And then this you already did. You did it over here. The same number that you did there, only in effect you're adding that number again, okay? And subtracting the 1 for this one, okay? And anyway, that comes up to be a negative 7/12 when you do all that stuff. But a minus is a plus, so that gives you 71/6 of a foot. So that's a little over 10 feet. The last time we came, well, it wasn't much. The other was 10 2/3 feet. This time it is almost 12 feet, not quite 12 feet. So 10 1/3 feet to 11 5/6 feet. Okay. So there is a difference there, the greater difference. And the reason it's not that much is because you're only going backwards for a very short time. Okay. And so therefore it's not a lot of area. The first time you took this area, subtracted this area from it, in effect. This time you're taking this area and adding this area to it. Okay, that's what you're doing to get total distance. Okay. Now, I didn't do all the entering it on the calculator, but that's what you would get. 71/6 of a foot, just short of 12 feet. The other one was just over 10 feet. Oh, that's the last, and it is. That's indeed the last example in 5.4. Homework exercises here would include either 5 or 7. They're both a Calc Chat. Any of the odds 9 through 33, a whole bunch of them there. They're all at Calc Chat, 17's at Calc View. So folks, if you don't have this book and you want to see some of these examples, do that. Go there. And by the way, I forgot to check this. No, none of the ones we did today were also at larsoncalculus.com. I was going to say if they were, you could actually see the ones that we were talking about. So any of the odds 9 through 33, they're all at Calc Chat, 17's at Calc View. Either 35 or 37, they're both at Calc Chat, 35's at Calc View. Any of the odds 39 to 43, they're all at Calc Chat, 41's at Calc View. 45 to 49, they're all at Calc Chat, 45's at Calc View. 51 to 55, they're all at Calc Chat, 51's at Calc View. Either 57 or 59, they're both at Calc Chat. And there is a thing called Buffin's needle experiment. I don't know really who Buffin was, but if that's something that you might be interested in chasing down, there may be a paper topic in there. Hint, get working on your paper, folks. We're using up time in the term now. Okay, let's move on. Do 61, it's both a Calc Chat and Calc View. Do 63, it's a Calc Chat. Do 65 is a Calc Chat. Then do any of the odds 67 to 73, they're all at Calc Chat, 69's at Calc View. Any of the odds 75 to 79, they're all at Calc Chat, 75's at Calc View. Any of the odds 81 to 85, they're all at Calc Chat. And then do any of the odds 87 to 91, they're all at Calc Chat. Then any of the odds 93 to 97, all at Calc Chat, 93 is at Calc View. You can explore doing 99 and or 101 if you'd like. That's up to you. 103 would be at Calc Chat. Now, I really don't care for the error analysis, but if you find them useful, go for them. Either 105 or 107, they're both at Calc Chat. What they've written in the book is wrong, and they ask you to find out where they made the error. I don't like them to put anything wrong in the book, but they put big red X's, so it's okay, I guess. Do 109. It's a true false. It should be at Calc Chat. 111 or 113 should both be at Calc Chat. 115 is one of those Putnam exam challenges. If you really feel like this is way too easy for you, try that one. And then there's a section project if you're interested in that. I'm not assigning that either. But we're now moving on to 5.5. So let me get out of this, in that slideshow. I'll just leave it alone for now and just change the a new share here to 5.5. Okay. And to me, 5.5 is a really fun section. Okay. Most people really enjoy doing these. Okay. We're still in chapter 5, integration. 5.5 is integration by substitution. Now, some of you who have already had this probably, this is old hat to you. But those who haven't had it yet, I don't think you'll find it's too hard to follow. So let's see where it's leading. Here are our objectives. There's a lot of them. Now, this pattern recognition to find an indefinite integral, yeah, that's fine. Change of variables to find the indefinite integral, yeah, that's going to be, to me, more precise. Use the general power rule for integration to find an indefinite integral. Yeah, we're kind of doing that all along. We'll use a change of variables, again, to evaluate a definite integral, not an indefinite integral. So the difference between this one and that one, this is indefinite, this is definite. And we'll evaluate a definite integral using the characteristics of even or odd functions, okay? So I don't really care for the pattern recognition, but if you do, it's fine. It's perfectly legitimate, but it seems like you're just doing some guessing first when you could really be a lot more certain of it. This section will study techniques for integrating composite functions. Now, basically, this is kind of like you're undoing a chain rule in differentiation. In a really stretch, that's what you're doing here. The discussion splits into two parts: pattern recognition, which is okay, it's perfectly fine, and change of variables, which I find is much more direct, and both techniques involve what they call a U substitution. They love U as your substitution. You can use any letter you want to, but they always use U substitution. I don't know why. With pattern recognition, you perform the substitution mentally, and with the change of variables, you write the substitution steps. I find it easier to do that. The role of substitution and integration is comparable to the role of chain rule and differentiation. You're undoing the chain rule. That's what I said earlier. So let's think back. Recall that for a differentiable functions, if you have y as some function of u, capital F of u, but u is some function of little g of x, the chain rule says d by dx of your ultimate independent variable. See, u is kind of an intermediate variable. It looks like it's independent here, but it becomes dependent there. So it goes back and forth between being independent and dependent. X is independent all the way around. So if you're taking the d by dx of your independent variable x, then you do, the chain rule says, take the derivative of the capital F, evaluate it at g of x, and then take the derivative of g, okay, and that gives it to you. So from the definition of an antiderivative, if you had this to begin with under a radical, then that's simply this. If this is in your, I'm sorry, I said under an integral, in an integral, if you recognize that this is a derivative here, and that's the derivative of the inner part of that derivative, then you can just say, oh, well then the antiderivative of this function evaluated at that function. Of course, with a plus c. You always have to put plus c if this is an indefinite integral. Now, that's if you recognize it. If you don't recognize it, just do a U substitution. That's the way to go. These results are summarized in the following theorem. The anti-differentiation of a composite function, if g is a function whose range is some interval I, okay, and let f be some function that is continuous on that same interval I. So g is a function whose range is I, those are the result variables, and f is a function that's continuous on those variables I when you turn them sideways, you might think. If g is differentiable on its domain, remember the I is the range, and f is the antiderivative of f, capital F is the antiderivative of some other function, little f on I, then the integral of f of g, g prime, well, the antiderivative of f, little f, is capital F. It's just as capital F evaluated at that g of x. plus c, of course, because of indefinite integral. Here's how you actually do it. Find that innermost function. Find the innermost function. Let that be u. Then du, in this case, it's going to be dg dx is g prime dx. Okay? That's your du. And then you undo this by antiderivative. That's your capital F of u, but u is g of x. You get that same answer. That's the way to go, folks. Okay? A u substitution. Now, example 1 is going to show how to apply that directly, and they say by recognizing the presence. Note that the composite functions of the integrand has an outside function f and an inside function g. That's what I was saying, the innermost function. Moreover, the derivative g prime is present as a factor in the integrand. That has to be there. So you have an outside function here, an inside function here, and the derivative of that inside function there. Okay? And if that's all met, then you take just the antiderivative of the outside function evaluated at the inside function. Okay? Sounds like a lot of blah, blah, blah. And you always add c because you're indefinite integral. So let's do it. Now, do I want to do the recognition thing? Not really. Here's what I suggest you do. Start off by saying, find the innermost function here, x squared plus 1. The outermost function is a squaring function. The innermost function is what's inside that squaring function, x squared plus 1. Let that be u. Let u equal x squared plus 1. I hope you're writing this down, folks. Please have a pencil and paper and write it down. Let u equal x squared plus 1. Then du, and this is written in differential form. Remember, du is 2x dx. Guess what? There's your 2x dx. So this is your du here, and this is u squared here, right? Because u was this part, squared du. Hey, write that down, and then you say, what's the antiderivative of u squared in terms of u? Well, it's u to the third over 2. Okay? So that would be u to the third over 2. Then go in and put back it, plus c, of course. Okay? And then go on and put this back in for u. X squared plus 1. So it'd be 1/3 x squared plus 1 raised to the third power plus c. There's your answer. So let's see how they did it. Now, if you like introducing a g of x into it and doing all this stuff, fine, go for it. I prefer just u, okay? Let u equal the innermost part, okay? X squared plus 1. Then du, or if you want to do g of x, that's fine too. That is derivative of x squared is 2x. I would put a dx out here because that's what you have up here. Du is equal to 2x dx, okay? Then, who cares about this again? Just we're going to write it down. It would be u squared du. That's what you're integrating. U squared du, that's u cubed over 3 plus c, okay? They're going to get around to that in a minute, but why go through all this pattern stuff? If you just do that directly, you're already there. You use the power rule for integration. That's what it did. U squared du would be u cubed over 3. That's what we got. And then they write it in here. And that's what I said. 1/3 x squared plus 1. That was your u cubed plus c. There's your answer. If you like the way the book did it, go for it. Use it. It's absolutely correct. If you do a u substitution, it's so much more direct in my mind. Okay? It just seems like that to me. So there's your answer, 1/3 x squared plus 1 cubed. Okay? Now it says try using the chain rule to check that the derivative of this thing is indeed what your integral was. Well, the derivative of this would be 3 times 1/3, which is 1, times this thing right here, squared, times the root of this, which is 2x. That's exactly what you had. This thing right here, x squared plus 1 squared, 2x dx. That's it. That's your original integral. Easy way to check it. And check it if you need to. Please do. I want you to give me right answers, not wrong answers. So check your answers, make sure they're right. Okay. The integrand in example 1 fits the pattern, which, so what? Okay, exactly. So you only had to recognize the pattern. You can extend that technique considerably using the constant multiple rule by factoring out that constant multiple if that helps you. Okay, and many integrands contain the essential part that the variable part of g prime are missing a constant multiple. So put it in, take it out, whatever makes sense. In such cases, you can multiply and divide by the necessary constant rule. And that's what example 3 is going to show. Well, guess what, folks? They skipped example 2. So let's go back a slide. And let's do example 2. Now, how are we doing on time? I don't have my watch. The battery ran out. Oh, we're at 1:40. We go till 2:25. So we got some time. So let's go back to my whiteboard and let's do example 2. Again, I've got to get this thing out of the way. You can't see it, but it's a taskbar, toolbar. It's doing nothing but blocking the way. All right, here's example 2. Find the integral, indefinite integral, of 5 that's a 5, not an e to the 5x, that is a 5, that is an x, dx. Now, after you've done these a while, you can probably just do that by sight. And I guess that's what they mean by the, whatever they called it, pattern recognition, okay? But until you're used to it, until you are confident in it, here's how I like to do this. Here's a constant. We could take it out if we wanted to, leave it in. I don't care, okay? Here's a function, okay? It's a composite function. It's an exponential function, but you're operating on an inner function, a product function, 5x, okay? So that's where I would immediately say, let, and this is how I do it. If you have a better way that you see better, by all means use it. Let u equal that inner portion. U equals 5x. That portion right up there. Then the very next statement is always a then. Okay, take a derivative of this. Only take a differential. Okay, take a differential. Here it would be du is equal to, and derivative of 5x is just 5. Differential, though, would be dx. Okay, and that's pretty straightforward. Du is 5 times dx. Okay, that you just took a derivative of each of those functions. That's in differential form. Now, what you see you've got up here is a 5 dx, that's your du, and this right here is a e to the u. So just rewrite this. This is equivalent to, you could put an equal sign and that would be fine, but that's equivalent to the integral of, remember the 5 dx was du, so I'm just going to write that down here, du And then the e to the 5x is just e to the u. Now the question I have for you is, what's the antiderivative of e to the u? Please someone tell me you know it. Anybody? It's easy, folks. It's the antiderivative of e to the u. My favorite function of all time. It's itself. It is e to the u. Because what's the derivative of e to the u? E to the u, okay? The u, you might say, okay? Now, but it's an indefinite integral, so we do put a plus c here. Okay, but this answer is in variable u. Our problem was in the variable x. So let's go back and plug in what u is. Well, the e is still an e. That hasn't changed. But u is 5x. So e to the 5x plus c. See how it is? It's pretty straightforward. It's pretty simple. You don't have to worry about a pattern recognition or G's and things like this. Just let your U do your working for you, okay? Now, if you want to check it, what's the derivative of this with respect to x? Well, derivative of e to the 5x is e to the 5x, but then the chain rule part says take the derivative of 5x, and that gives you a 5. And then derivative of c is 0. So you get 5e to the 5x. That's exactly what you've got in here. That's it. That is it. That is example 2. The answer is e to the 5x plus c. Now, they have at the bottom of page 233 what they call exploration, recognizing some patterns. Okay? Now, this would take a long time to write out, so I'm not going to do that. Now, it seems like maybe all but one or two of you probably do have books, so hopefully you're looking at the bottom of page 333. I'm going to hold this up for the rest of you to see. This is what we're talking about here. Okay? I hope you can see that. Okay? Now let's see what they call pattern recognitions are. If your integral is 2x times x squared plus 1 to the 4th power, the outer function is the 4th power. The inner function is x squared plus 1. The derivative of x squared plus 1 is your 2x. That's what you've got right there in front of you. So, yeah, that's very definitely a pattern. If your second one there was the integral of 3x squared times the radical x cubed plus 1, the square root of x cubed plus 1, the innermost function is x cubed plus 1. Its derivative is 3x squared. There it is on the outside. Okay? Then we have another one, the integral of secant squared x times tangent x plus 3. Okay? Well, in this one, derivative of tangent is secant squared, so there you see it's on the outside. So leave it there. I mean, it's fine. Let that be your u. Okay? Now, the next three are a little bit more involved. The first one is the integral of x times x squared plus 1 raised to the 4th power. Well, the innermost function is x squared plus 1. Its derivative is 2x. You don't have a 2x on the outside, you only have an x. So multiply it by 2, but then on the outside of the integral, take 1/2. That's what they're talking about, multiplying and dividing by 1/2. Same thing with the next one, the integral of x squared times the square root of x cubed plus 1. Innermost function is x cubed plus 1. Square root of the derivative of that is 3x squared. On the outside, you only have x squared. Put a 3 in front of that, but put a 1/3 on the outside. That's what they mean, multiplying and dividing by the same number. The next one was the integral of 2 secant squared x times tangent x plus 3. Well, again, we know the derivative of tangent x is secant squared x. You have a 2 secant squared x. Yank that 2 and put it on the outside. You don't need it on the inside. Put it on the outside. And you've got your derivative on the inside. That's what they're meaning, I guess, with their pattern recognition. Basically, it's U substitution. I don't see why they make a difference there. So let's move on to example 3, I think. Oh, well, I can't do that. Let me go back and go back to the square we did, the share we did before, 5.5. Okay, from current slide. Okay, that was the end of example 1. They skipped example 2 and start talking about example 3. So here's example 3. Now, please have your pencil and paper handy. I hope you have it there in front of you. Let's do it. Okay? What do I look for? I look for my cursor. There it is. Okay. Here's the innermost function, x squared plus 1. So let u equal x squared plus 1. Well, then the next step is always then du is equal to 2x dx, right? Written in differential form. Well, up here, all you have is an x dx. Well, I want it to be a 2x dx. So you could write a 2 in here, but if you do that, put a 1/2 out here, because 1/2 of 2 is 1. You haven't changed anything, okay? Now, that's one way of doing it, and that's a perfectly good way. I'm going to show you a slightly different way. It's the same thing, but it just sort of skips a step or two. But I'll worry about that later, okay? Now, so what you have now, you have the 1/2 on the outside, remember, because you put a 2 on the inside, and the 2x dx is your du, because you said let u be x squared plus 1, so du was 2x dx. So you got a 2 there, a dx here, so there's your du, a 1/2 on the outside, and all you've got left on the inside is 1/2 of the integral of u squared du. And we already know what the antiderivative of u squared is. It's u cubed over 3. Well, you had a 1 over 2 on the outside already. Now you have a 1 over 3 on the outside as well. So that'd be 1/6 u to the 3rd, okay, and u cubed, okay? Now, go back and plug in what u is. U is, or u are, x squared plus 1. So it's 1/6 x squared plus 1 cubed. Plus c, of course. It's an indefinite integral. Okay, let's see how they did it. Similar to the integral in example 1, except the integrand is missing that factor of 2. So all you do is put it in, okay? Now they put it both on the inside. That's okay. It seems like that's just a wasted step there. Why don't you put the 2 on the inside with the x here and just put a 1/2 on the outside? Why put them both on the inside and then the next step you take the 1/2 on the outside? I don't know, okay? To me, it's easier just to go straight here. And now you have, forget about f of g and g prime, unless you just like thinking that way. This is now 1/2 the integral of u squared du, okay? And that is u the cubed over 3, okay? And there's your u cubed over 3, okay? They left it as x squared plus 1 cubed over 3. That's fine. And then that factors to, or results to be 1/2 of 1/3 is 1/6 x squared plus 1. That's your u cubed plus c. Okay, done. That's it. Okay. If you like the way they're doing it, go for it. It's fine. It's perfectly correct. Just seems like to me it's so much easier to do a u substitution. So that was example 3. Now we're going to, and this is what I've been doing, change of variables for indefinite integrals. Okay, Without with a formal change of variables, you completely rewrite the integral in terms of u and du, or any other convenient variable. They love u substitutions. It can be a v, it can be a y, it can be a z, it can be a stickman. It can be anything you want it to be. Just don't have it your original variable. You don't have two x's in there that mean different things, okay? Although this procedure can involve more written steps, I think it involves fewer written steps, and the pattern recognition is useful for complicated integrands, which would be complicated integrals too. The change of variables technique used the Leibniz notation for the differential, okay? That's what I was using. That is, if u is equal to g of x, then du is g prime of x dx, okay? And the integral takes the form of f of u du, and then you just integrate that, get what the antiderivative is, and then plug back in what u is. You already said that, plug it back in, and you're there. All right, so here's example 4. Okay, now this is doing it their way. Okay, well, no, I mean, it's the way I've been doing too. Okay, what you have, the outer function is a square root function, the inner function is this linear function. Okay, so let u be 2x minus 1. Write that down. Let u equal 2x minus 1. Your next step is always then du. Just take derivative of u as du. And what's the derivative of 2x? 2 dx. Okay. Now, you might look at this and say, I don't have a 2 dx. I'll just have a dx. Well, you could write a 2 in here and then write a 1/2 in front if you want to do it that way. Perfectly fine. So let's see. Let's just take a step at a time. So first, let u be the innermost function, which is 2x minus 1, just like I said, okay? Then the next step is always take a derivative. Du is equal to 2 dx. Derivative of 1 is 0. So du is equal to 2 dx. Now you look at this and say, well, up here, and you can do it either one of two ways. Now they're doing it the way I sort of like to do it. They don't have a 2 dx up here, they just have a dx. So if du is equal to 2 dx, divide both sides by 2. That's the same way as what we were saying before. And then you have du over 2 is equal to dx. Okay? Well, this then would become the square root of u, because u was 2x minus 1, du over 2. But I wouldn't put the over 2 here. Put the 1/2 out here. Be 1/2 the integral. I would write this as x to the 1/2, u to the 1/2 du. That's so much easier to integrate, okay? And that's what they did here. 1/2, they pulled the 1/2 on the outside, the integral of u to the 1/2 du. That's just a power rule, just a power rule. The antiderivative of this would be u to the, add 1 to this, 3/2. Divide by 3/2, which is the same as multiplying by 2/3. Multiply by 2/3, the 2's go out, and you're left with a 1/3 here. So it would be a 1/3 u to the 3/2 plus c. And they haven't done all that stuff yet, but there it is, 1/3 u to the 3/2 plus c. Then go back and plug in what u is. U was, remind me, 2x minus 1, I think it was. Put that back in, 1/3 2x minus 1 raised to the 3/2 power plus c. There's your answer. Done for you. Almost. I mean, it minimizes any struggle. It just do what it tells you to do. If you want to check it, let's take a derivative of this thing. 2/3 of 1/2 would be, of 1/3 would be 1/2, because the 3's would cancel out. 1/2 2x minus 1 to the 1/2, and when you reduce this by 1, times 2, there wipes out your 1/2, the 2 wipes out, and you have 2x minus 1 to the 1/2 plus c, which is the square root of 2x minus 1. Exactly what we started with. All right, that was example 4. Okay, let's us do example 5. They do the easy one for you and then have you do the one that's a little bit, it's not all that much harder, but may have a little bit more to do with it. So let's clear the screen. Does anyone need that old one any longer? Okay. So let's do example 5. Now, by the way, this one is at larsoncalculus.com. So if any of you don't have this text and you want to see this example, not done in my scratchy whiteboard, want to see how the book does it, by all means, go for it. So here is what they're asking for. Okay, they're asking for the integral, surprise, 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 of x okay. They did throw a curve on you. Times the square root of 2x minus 1. This is a very different problem. It looks similar, but it is very, very different. Okay? Now, this doesn't fit a pattern recognition thing at all. Okay? That's why I found that sort of useless. Not totally useless, but not all that beneficial. Again, don't know where to start, so let's start with the u substitution. Find the innermost part of the most complicated part of the problem. That's your 2x minus 1. So let's start there. Let u, even though it's hard to write, and it's ugly writing too, let u equal 2x minus 1, the innermost part, 2x minus 1. Okay? So let's do, next step is always then. I like to write the then down, even though I don't like to write it when I'm having to use a keypad. But on paper, pencil and paper, I always write it down. So I'm going to do it here too. Then take a derivative. du, only you're taking a differential, not a derivative, is equal to derivative of 2x is 2. Differential of it is 2 dx. Derivative of minus 1 is 0. Now that's exactly like we had before. Except, Houston, we have a problem. Up here we have x dx, not 2 dx. And you can't go around dividing out an x. You know, you don't do that. You only divide out numbers. So how in the world are we going to do this? Well, let's go back to our first definition here and see what this tells us. Let's solve this for x. Okay? And that would mean adding 1 to both sides. So that would, again, I'm going to flip sides on you here. 2x, okay, because the plus 1 minus 1 adds to 0, is equal to u plus 1. That's not bad, is it? And then divide both sides by 2. So what is x? X is u plus 1 over 2. So let's go back to our integral up here. Goodness gracious, this is ugly. Okay, and what do we have here, folks? Okay, your x is u plus 1 over 2. So let's take the 1/2 outside that integral. We may want it back inside later, but we'll leave it outside for now, times the integral of u plus 1 that's your x, u plus 1 over 2. We got it right here, okay? Times, and I'm going to write this in exponential notation, your 2 x minus 1 was just your u. So that's going to be u to the 1/2 power, right? I don't like the radical, so I'll write it in exponential notation, okay? And then you have, here's a dx. All you have is you don't have a 2dx, so let's divide out our 2's here. So you make your dx du over 2. We'll put the du inside the radical, inside the integral, and put the 2 on the outside. So this actually is now 1/2 of a 1/2. So that's going to be a 1/4. Okay, that's a little messy, but writing with my finger is about the best I can do. So now let's see what we've got. This integral is now 1/4, because 2 times 2 is 4, and they're both in the denominator. Okay, the integral of, well, this is, in a sense, kind of like a polynomial, only it's not. It's radicals, but you can, it's still an easy thing to this, is u to the 2/2 times u to the 1/2, distribute the u to the 1/2 across both terms here. U to the 1/2 times u to the 2/2 is u to the 3/2, right? Plus u to the 1/2 times 1 is u to the 1/2. That's just some fairly simple arithmetic there. And this is all times du. Oops, that's an ugly d, isn't it? Okay. Now, you could put that in parentheses if you want to. It's just hard for me to write parentheses. This is going to be 1/4. Okay. Now, what's the antiderivative of u to the 2 or the 3/2? Anyone want to help me out there? Antiderivative of u to the 3/2. It's a simple power rule. You increase this by 1. Well, 1 is 2/2. 3/2 plus 2/2 is 5/2. Okay? And then you either divide by the 5/2, but I prefer calling that multiplying by 2/5. It's just easier for me to do. That's supposed to be a 5. It's not a very pretty one. Okay, plus. Okay. Now here we have antiderivative of u to the 1/2. Again, power rule. Increase this by 1. That would be 2/2. 1/2 plus 2/2 is 3/2. So that's going to be a u to the 3/2 power. I can't write. 3/2 power. And divide that by 3/2, or I prefer multiplying it by 2/3. The first one's a 5, that one's a 3. Okay? I'm going to close this off and put my plus c out here because it's an indefinite integral. Okay? But there's the antiderivative of it. All right. Now, just a couple things to note. You don't have to do it now, but I like to go and get rid of it. You see the denominator here is a 4. Both of these numerators have 2's in them. So why don't we just factor those out, or divide those out, and divide 2 into each of those, and that will give us a 2 down here. Okay? So this is going to be 1/2 of 1/5. That looks like to me to be 1/10. I'm sort of skipping some steps here because it's so hard for me to write on the keypad here. U to the 5/2 power. Well, what is U? U is, or U are, 2x minus 1. So that'd be 1/10 2x minus 1 to the 5/2 power. This is so hard to get this thing to move where I want it to. Okay. Now that was 1/2 times 5. 1/2 times 1/3 would be 1 plus 1/6. That 1/2 was outside both of these, remember, don't forget that. And this is u, but u again is 2x minus 1. This time it's to the 3/2 power. And then finally we have our plus c, because this is an indefinite integral to begin with. So there you have it. Now I have a feeling maybe in the book they'll pull the 1/2 or left the 1/2 out front. The 1/2 times bracket 2x minus 1 to the 5/2 over 5 plus 2x minus 1 to the 3/2 over 3. I don't know how they're going to leave it, but either one of those answers is perfectly fine. Let's see how they did write it. No, they actually, no. Yeah, they did it the same way I did. 1/10 2x minus 1 to the 5/2 power plus 1/6 2x minus 1 to the 3/2 power plus c. All right, good deal. Any questions on that? Any at all? Okay. Now, I do believe, I hope, the next one's on the PowerPoint. Let's go back and see. I forgot to notice before for 5.5. And let's go back to current slide, wherever that is. All right, that was example. We did example 5. Let's see if they have example 6. No, they don't. Sorry about that. Let's go back to the drawing board. Okay, because this guidelines is after example 6. So let's do example 6. Now, this may be all we have time for. We have what? 14 minutes. Let's see if we can get it done in 14 minutes. All right, to erase this one? Any objections? Speak now, forever hold your peace, because it's going. Gone. Okay, here's example 6. Here's the integral. It's an ugly integral. Sine squared three x cosine 3x dx. Now, this is a little bit different kind of a problem. Okay, now what my rule was before was find the innermost part of the most complicated part of your problem. And by that definition, the most complicated part is the sine squared. That's the outermost. The innermost part of that would be the 3x. And that certainly is a good place to start. Now, the trouble is you're probably going to have 2 substitutions here. So it depends on how much you like u and where you want to put your u, but why not start with u? So let's start again. Let u, and you don't have to do it this way, but I'm going to do it this way because that's following the rules, okay? Let u equal 3x. Okay? Then that always follows the let is the then. I feel like someone who's basically almost illiterate and can't write. Okay, this is what it seems like. Take a derivative of both sides. This will be a du on this side is equal to 3 times dx. Everybody understand that? I sure like more participation than this, folks. Y'all are awfully quiet. Okay. Well, we look at here, we don't have a 3dx here. What's that? Okay, good. All right. We don't have a 3dx, we just have a dx. So let's get rid of the 3, not just throw it out, but let's divide it away. Okay. But then you'll have to put it over here with the du, which we can do. Now the dx's, the 3's are going from this side, they're over here in the denominator, so you have a dx. So we're going to be okay with that. Okay. But what would we have next? Now I'm going to write it out even though it's painful to do so. This would go to, okay, let's pull out the 1/3. See the one, we don't need that inside the radicals. So let's do the 1/3 here. And here's your integral. And then we have sine squared u, because u was 3x, that's why we did it, cosine u, that's ugly, isn't it? That's even uglier. And then we have our du because we pulled the 1/3 out already. Okay, so now that's what we've got. Well, Houston, we still have a problem. We have two functions in here. The most complicated function is your squaring function. That's the outer function. The inner function of that now is sine. So let's do another substitution, okay? And since I've already used u, let's go with v. Let's let, now you don't have to do it this way. You might see the answer already, write it down, that's perfectly fine. But let's let now v equal the next inner function from the squaring function, which is the sine function. And that's sine u. Okay? And of course, what follows that is then dv someone's keeping up with my time, aren't you? Okay, good. What is dv? If v is sine u, what is dv? What's the derivative of sine? Come on, we're running out of time. Derivative of sine is cosine, right? Cosine u du. We're doing it in differential form, so there's your du. And guess what we've got here? We've got a cosine u du here. We have a cosine u du here. So we will rewrite that integral up there as being 1/3 the integral of, and sine u was your v, so this is simply just a v squared, because the sine was squared, so that's v squared, and the cosine u du is your dv, v squared dv. And I think I can even do that one. It's going to be a 1/3. And what's the antiderivative? That's supposed to be a 3 there. It's ugly. What's the antiderivative of v squared? Anybody? Increase that by 1 and divide by that new exponent. That would be v cubed over 3. And then you'd have a plus c, of course. We'll write it down now and it'll hang around for us forever. So simplifying that a little bit, that would be 1/9, because 1/3 of 1/3 is 1/9 v cubed. But what is v? That's sine squared u. I mean sine u. So v is sine u, and you're cubing that, so that would be sine cubed u sine 1/9 of sine cubed u plus c. Don't forget your plus c. But what is u? U was 3x. So this will then be equal to 1/9. See if I make that 9 look a little bit better. Just a tad of sine cubed of 3x, because the u was 3x plus c. Whew, I think we're through with that one. Let's see what they got in the book. Example 6, 1/9 sine cubed 3x plus c. Yes, got it done. All right, and with time to spare, okay? So what we'll do now with that little bit of time we've got to spare is go back to our PowerPoint from the current slide, which is where we were a minute ago. And here's where that is. The steps used for integration by substitution are summarized in the following guidelines. I'll tell you which of these I like and which I don't. Okay, guidelines for making a change of variables. Choose a substitution u is equal to g of x. Okay, now you don't write g of x down. What you do is find the innermost part of the most complicated part of your integram. Most complicated part usually have something done to it. Find the innermost part of that complicated part. Let that be g of x. Don't write down g of x. Let u equal that innermost part. Usually it's best to choose, like I said, the inner part of the composite function or the most complicated part, such as a quantity raised to a power or whatever it happens to be. So as soon as you let u equal whatever that function is, then do a du is the derivative of that function times dx. Okay, that's what we did the second step. First step, let u equal whatever that innermost part was. Second step, take a derivative. Du is equal to whatever the derivative of that is, dx. Always the d's go together. If you have a du, you better have a dx. If a dv, you better have a du. Okay? Now, rewrite the integral in terms of that new variable u. Okay? And that's what we were doing. Then, if you can, find the resulting integral in terms of u. Do the integration. If you can't, do another step and do another substitution. Finally, once you've done the integration, then replace the u by that, whatever that innermost function was to begin with, 2x plus minus 3, whatever it was, put that back in instead of the u, and check your answer by differentiating. We didn't do that on all of them, but that's pretty easy to do. All right, we did it on some. So there's our steps. Okay, how are we doing on time? Oh, we've still got some time. So let's move on to the general power rule for integration. Man, I thought we were already doing this, okay? One of the most common used substitutions involves quantities in the integrand that are raised to a power. Because of the importance of this type of substitution, it is given a special name, the general power rule for integration. I see no reason for a special name, but it's fine if you want to name it that way. You can name it Sue, I don't care. The general power rule for integration, if g is a differentiable function of x, and you have this g raised to some power, but then you just happen to have the g prime after that, whatever that function was, raised to a power, and a g prime after that, then all you do is take that g to the one, raise it one power, divide by that new power, plus c, there it is, as long as that n right here is not a minus 1. If it is a minus 1, that's going to be a log of g. Okay. Equivalently, if u is equal to g of x, that's how I would do it because this is the innermost function here. U equal g of x, then the integral would be u raised to the n times du. That'd be u to the n plus 1 over n plus 1 plus c. That's again, as long as that n is not equal to negative 1. Okay, if it is, the answer is going to be a log function, natural log. It's not going to be a power function. Okay. Now, do we have time for example 7? I'm just going to make a guess not. Okay, I'm sorry we lost time in the middle of class there when the internet just went out. So we'll begin next time with example 7 on page 337. Okay, homework exercises for this section include either 5 or 7. They're both at Calc Chat. 5's at Calc View. Any of the odds 9 through 27, they're all at Calc Chat. 15's at Calc View. For some reason, they're sticking in a differential equation. I don't think it's too bad. Either 29 or 31, they're both at Calc Chat. 29's at Calc View. And here they're giving a slope field. And why they're doing that here, I'm not sure. But if you want to try this, you can. It's pretty simple. 33 should be at Calc View. Then they get back to actually doing integrals. Any of the odds 35 through 55. Okay? They're all at Calc Chat. 41's at Calc View. Okay, I think you can do any of the odds 57 to 63. They're all at Calc Chat. 59's at Calc View. I think you can do, this is similar to one we did just a couple of examples ago, 65 to 71. They're all at Calc Chat. 65's at Calc View. Stop there because we haven't done the definite integrals yet. We'll get there shortly. Very next thing. Okay, so stop at around 71. If you don't get that far, that's okay. We will have more time to do those. Any question? And it is time to go. So if you don't have any question, I'm going to have to stop the sharing. And with stopping the sharing, I'll also end the Zoom. So if I don't hear anything, take care. We'll see you on Monday. Have a good weekend. Okay?